Okay, question 10, we've got one on hearing and frequency and the intensity of the sound. Describe two differences between the hearing responses of a human and a mouse. So there is the mouse. I don't know what to talk about the bird yet. Let's change my colour, if it'll let me. There's my, whoops. Oh dear, A-side, you messed that up. Oh, do you know, I thought I'd changed the colour. Let's go again. There's the human. Don't know why I wasted so much time trying to pick the different colours, because I've now got to do it again. Okay, so describe two differences. Well, there's a range of difference here. We can see that humans are better at low frequencies, and the mice, so their minima here, okay, they are able to detect low frequency sounds a lot better than the mouse. This is in kilohertz. We can see that so they can do low frequency. The mouse has done better at high frequency. And the next thing to note is the human just has one minimum, whereas the mouse has two minimum values. It's got a value here and a value here. And we can just reword that however we want. It looks like a tricky question, but it's actually relatively easy. So mice are more sensitive to higher frequencies. Fab, we've got that there. Humans are more sensitive to lower frequencies. Love it. Mice have two minima. Humans have one. And it was any two of those three statements. A farmer wants to use an alarm to scare away birds. State which frequency is the most effective. Well, it's going to be the one that they're most sensitive to. So if I doodle all of this away, we're just going to find out the minima for the bird. That's the one that they're most sensitive to. And I've got that as around 2 kilohertz. So the frequency would be 2.5, 2-ish kilohertz. I don't really know what the mark scheme says in that, but I know that is right. State the reason for your choice. Birds are most sensitive to this frequency. It's just making sure you can interpret a graph. Describe the difference between infrasound and ultrasound. I've taught you those values. 20 to 20,000 is the range for human hearing. And we know infrasound is this way in terms of elephants communicating with their feet on the ground. And ultrasound is above it, bats, and you know that dogs and things like that can go above ultrasound. So ultrasound is sound above 20,000 hertz or 20 kilohertz, mark. Infrasound is below 20 hertz. So a nice easy answer to that. This one we've done quite a bit. So this one now, because we've got the sound wave going there and back, we've got a calculation using shoot Donald Trump twice. So we need two lots of the difference because it's got to go there and back. So D plus another D equals 2D. So now that we're pretty happy with that, we've now got to, they reflect off the seafloor, got it. They travel at 1,500 meters per second. Love that, no unit change there. 48 milliseconds though, got to divide that by 1,000. Calculate the depth of the water. So we're just going to plug it into that equation. So we know, I'm going to rearrange this so that I'm not left with 2D on the one side. So D equals S times T over 2. Plug in the values, 1,500. 0.048 when I've divided by 1,000, divided by 2, and we've got our answer of 36 meters. I think that's quite a nice easy 2 marks actually. The next one, explain how vibrations from earthquakes may be used to study the core of the Earth. So I've gone over this before. So we know that there's two types of waves, P waves and S waves, so primary waves and secondary waves. We know that these are faster. We know that these can travel through solids and liquids. These can go through solids only. So what we can do now, what we can do now is talk about this. Well, the crucial part is, if we were to have, say, an earthquake here, and we can have a sensor over there and a sensor over there. So I'll just mark some sensors, obviously they're on the Earth. And what's going to happen is, as the waves go through different layers, they're going to refract. So that's the first part. So we've got to talk about them refracting. How much they refract tells us the density difference. All right, so I'll put the change in density, change in rho. So change in rho. So that's the first part. So we're going to talk about refraction and the change in density. The next part is this idea that we therefore know that the outer core is liquid because we cannot sense. There's a shadow for the S waves on the other side of the planet. And we just want to word those nicely. And I've gone over this a couple of times now in terms of past papers, so I hope this helps again. So first part then, seismometers can measure the degree of refraction or the amount of refraction at each boundary layer. This can give us information on the density differences, and you can see I've bolded that down 2 marks. So I can measure the refraction, that tells me the density differences, which enables us to see the layers and the makeup of those layers. The next part is S waves can pass through solids only, P waves can pass through solids and liquids, and then there's an S wave shadow on the opposite side of the Earth, and this proves that the outer core is liquid, because obviously we ain't taking a trip there anytime soon. And that is it, guys.